Hey everyone, Houston Math Prep here. We're going to talk about multivariable functions in this video, what it means for something to be a function of more than one variable, and how to think about domains of these kinds of functions. When we talked about a function in single variable calculus, or even pre-calculus, when we had y as a function of one variable x, the graph of that function was some kind of one-dimensional curve in the xy plane, or in 2D space. And when we said that y is a function of x, that gave us information about the output of that function. That when we put in an x value, we'd only get out of it a single y value. When we're looking at a graph, you might remember that we could tell if y was a function of x by using the vertical line test, seeing if every vertical line through the graph would only intersect the graph once. Moving ahead now to z equals f of x comma y, which tells us that z is now a function of two variables, x and y. The notation tells us what's going to happen here. When we have y as just a function of x, then we plug in x values, and the function will give us y values, and our domain is really an interval or intervals, some set of values on the x-axis. If we have z as a function of x and y, this means that in order to get z values, we'll usually be plugging in both x and y values. In other words, plugging in an ordered pair, x comma y. So if we're plugging in ordered pairs, then our domain for z as a function of x and y is actually a set of points in the xy plane. So where we might have been asked before to sketch a domain on a number line for a single variable function, now, when asked to sketch the domain of a function of two variables, we'll need to sketch that domain in the xy plane. Some other important geometric differences that we want to point out if we have z as a function of two variables, x and y. The graph of a function of two variables will be some two-dimensional surface inside of three-dimensional space. If we're able to visualize the graph of a surface in 3D space, we can still think of the vertical line test being able to tell us if something's a function of x and y. Obviously, in 3D space, our vertical line test will now run in the z direction, but the idea is still the same, that if every vertical line through the graph of the function would only intersect the graph once, then we know z is a function of x and y. If we look at a sphere, which we're probably pretty familiar with already, a sphere is a 2D surface inside 3D space. Here I even have a specific equation I've written for my sphere. But a sphere is not a function of x and y. You can see it's pretty easy to find a place where we can draw a vertical line through the sphere that touches the sphere more than once. If we take our equation for the sphere and solve it for z, you get an idea of why this is not a function. Moving x and y terms to the other side and solving for z, we would end up with z being equal to this plus or minus square root you see here. So just by looking at this, you can tell that we're very likely to get two different z values if we plug in an x and a y due to this plus minus out here. Let's do something with this sphere, though, that's similar to something we might have done in pre-calculus with a circle. If we take this sphere, which is not a function, and look at these plus minus cases separately. So first looking at the positive case, this will give us the top half of the sphere, an upper hemisphere, which would now pass a vertical line test in 3D space. And now let's start looking a little bit more at the idea of domain as well here. We'll work several examples of finding domain here in just a minute, but I think it's important to start trying to see how domain works, and this is a good time to do it. We can see the domain for this function of x and y if we imagine all of the points in the xy plane as the shadow that this hemisphere would cast on the plane from above. Since you can probably tell here that our hemisphere has a radius of 3 and it's centered at the origin, our domain in the xy plane will be a solid disk of radius 3. So this tells us that if we plug in any ordered pair in this region of the xy plane into the function, we should get a defined z value. If we attempt to plug in some point in the xy plane outside of this region, we won't get a defined real number value for z. You can see why that might be, since it would make the quantity under the square root a negative number, and square roots of negative numbers are not real number values. We can see a similar thing with the negative case of our plus minus situation here. This time the graph is a lower hemisphere, so the bottom half of our sphere. You can see this is going to pass our vertical line test in R3. Visualizing domain here, this function actually has the same domain as the upper hemisphere, since we're dealing with the same formula under the square root. Remember that the domain is a region in the xy plane, so we actually want to visualize the domain as a shadow this hemisphere would cast on the plane from below. So we get the same solid disk of radius 3 here, and an overall way of thinking about domain for these functions of two variables is really if we vertically projected all of the surface for our function onto the xy plane, whether from above or below, or some of the points are already directly on the xy plane, that will give us our domain for our function. Now we're going to work through some examples of finding domain for a function of two variables and also sketching that domain in the xy plane. So here our first example, we want to sketch the domain for the function f of xy is equal to the square root of x plus the square root of y. When we look at this formula for the function, we can see that we have some things under square roots, and square roots have restrictions on them if we want real values out of them, right? So things inside of square roots really need to be non-negative, right? Those things that are in there, so non-negative, which is different than positive, right? We can take the square root of 0. So we just want things to be not negative. They can be 0 or they can be positive. So one way we would say that is that inside this root here, this x, this needs to be positive, would be greater than 0, and it could also be equal to 0. So x really needs to be greater than or equal to 0. That would make it not negative. The same thing's going to happen here for the y under this square root. It needs to be non-negative as well. So we also need y to be either greater than 0, in other words positive, or exactly 0, but it can't be less than 0. That would make that negative, and we can't take the square root of a negative number and get a real value. So these are our two conditions to get some real value out of our function. X and y must both be greater than or equal to 0. So we'll go ahead and set up our domain statement, and we'll say that the domain will say capital D is equal to, we're going to put in curly brackets because this is a set of things. Now the domain is a set of points, right? So the first thing that we'll write is we'll say the set of all x comma y ordered pairs, right? Points in the xy plane. We usually draw a vertical line. Sometimes you'll see people write a colon here. This says such that, and then the requirements for this point need to follow after that. So x and y both need to be greater than or equal to 0. So we'll just say here then x greater than or equal to 0, comma, y also greater than or equal to 0. Okay, so this reads that the domain is the set of all points such that x is greater than or equal to 0 and y is greater than or equal to 0. Now if we want to sketch this region in the xy plane, so think about everywhere where x is positive or 0 and everywhere y is positive or 0. If we just took the positive cases, x and y both positive, that's going to be in quadrant 1. But now it's also the case that x and y could be 0. So not just quadrant 1 here, we can actually be on the borderline, on the boundary of those quadrants as well. So really, as long as we are in quadrant 1, or we are on this positive y-axis, or we're on this positive x-axis, and the origin would count as well, right? Because that would mean x and y are both equal to 0, and that's okay. So as long as we're in quadrant 1, or on an axis that borders quadrant 1, then that is the sketch of our domain in the xy plane. Let's take a look at another one here. We have another square root function here, so same idea. We want to sketch the domain for the function. Our function of x and y this time is the square root of 4 minus x squared minus y. Now you'll notice that this is all one square root this time. So really what we just need with this is we need this entire thing underneath the square root to be non-negative, okay? In other words, we need all of this under here, this 4 minus x squared minus y, to be greater than or equal to 0. It can be 0 or it can be greater than 0, meaning it's positive. Now, if we want to sketch this, we might do some rearranging, right? So think about maybe if we put the y on the other side, that would give us 4 minus x squared is greater than or equal to y. Or we could sort of turn this around. If you're used to seeing y on the left side, that would say y is less than or equal to 4 minus x squared. And so we can write our set notation here. We can say our domain is going to be the set of all points x comma y in the plane such that y is less than or equal to 4 minus x squared. Now remember, this is going to be a region in the plane, so what we'll do maybe is focus on the y equal to 4 minus x squared part, and then we'll figure out which side we need to shade of that graph based on this less than. So y equal to 4 minus x squared, that's going to be a parabola. It has an intercept of 4 here. And because it's minus x squared, we know it's going to open in the downward direction in the xy plane. Actually, to get 0 here, it turns out these intercepts are going to be at 2 and negative 2 here. So we'll have a parabola, vertex at 0, 4. That goes through those 2 and negative 2 points on the x-axis. And so that is part of the domain because we have our equal to here. The less than part, that's going to be all the points that are below that in terms of y. So we'll actually be shading below this parabola instead of above. And so that is our domain in the xy plane for this function of x and y. Moving on to another example, we're going to sketch the domain for the function f of xy equal to 1 over x plus y. Now this doesn't have any square roots in it, but it does have another restriction that we need to deal with. We have a fraction here, and when we have a fraction, that means we have division, and we don't ever want our denominator to be 0. So whatever is in the denominator should not be equal to 0, because we can't have divide by 0 in math. It is undefined. So our domain for this will be whenever the denominator is not equal to 0. So we'll set up x plus y should not be equal to 0. And now how do we go about seeing this in the xy plane? Well, let's sort of treat this not equal to like an equal to for now, and then we'll just remember that it's the opposite of that, right? So if we were going to, let's say, solve this for y, we might subtract the x over to the other side. That would give us that y is not equal to negative x. And so this is our statement for the domain. So we'll go ahead and say that our domain for this function is going to be the set of all points in the xy plane, all x comma y points, such that y is not equal to negative x. If we think about sketching this, so again, let's go ahead and think about what just y equals negative x looks like, and then we know it's everything besides that. So y equals negative x, this is going to be actually, if we think of this as an equal to, this would be a line through the origin, and it has slope negative 1, y equals negative x. So in the equal to case, we would actually get a line that looks something like this. This would be y equals negative x, but we actually want it to be everything besides that line. So what we'll need to do is actually go ahead and say we don't want this. So I'm going to go ahead and make this a dashed line so that I can say that this is not part of my domain. So everything on this side of the line in 2D space is part of the domain, and everything on this side of the line in 2D space is part of the domain as well, but not the line in particular. So this is actually our domain sketched in the plane, everything except this line through the origin with slope negative 1. If we look at our next example here, we have our function. We're going to sketch the domain of 1 over the square root of 1 minus x squared minus y squared. So we actually have two operations that have a restriction on them, right? So we have this square root idea. So I'll point to the square root bar here. The square root idea, that needs to be non-negative, whatever's in there. So if I write that down, that means everything in the square root must be greater than or equal to 0. So we'll say 1 minus x squared minus y squared, non-negative, greater than or equal to 0. Now, additionally, we have 1 divided by this expression here. So I know that this expression, this entire thing in the denominator, should not be equal to 0, right? Not 0. We don't want divide by 0. So that tells me that this entire denominator, the square root of 1 minus x squared minus y squared, should actually not be equal to 0. And I have two restrictions here. And it actually turns out that this one here on the bottom interferes a little bit with this one on the top. If I go ahead and make this a little clearer, maybe by squaring both sides here, if I square both sides of this, that would say 1 minus x squared minus y squared should not be equal to 0. And so think about what we're saying. We're saying up here, 1 minus x squared minus y squared should be greater than or equal to 0. And this one down here says, well, the 1 minus x squared minus y squared cannot be equal to 0. So this part right here actually tells me that I do not want this equal to, so this quantity inside of the root had a certain amount of restrictions on it, but then because of the way this was in the denominator, we actually get some additional restriction on it, meaning that this stuff here cannot actually be equal to 0. It doesn't work because we have a denominator as well. So now we have this expression. Let's go ahead and work from there. So 1 minus x squared minus y squared must be greater than 0. If I go ahead and move my quadratic terms over to the right side, we'll add those over. That'll give us 1 is greater than x squared, positive, plus y squared. If we turn this around, if you'd like to see your variables on the left side, you can. That would be x squared plus y squared is less than 1. And if we think of this now as equal to 1, just to get an idea of the shape, x squared plus y squared equal to 1, that would be the unit circle, right? Circle with radius 1, centered at the origin. So let's go ahead and at least sketch the equal to part. So let's say that has a radius of 1 there. Now again, going back to this inequality, you'll notice we don't have an equal bar there, so actually being on the circle is not what we want. So we are actually going to take our circle and go ahead and make it a dashed or a dotted circle, saying that we don't want to be exactly on the circle. And this less than actually tells us that we want to be on the inside of the circle. When we have a closed curve here, this less than is going to give us inside of the circle being what we want. Greater than would be outside of the circle. So this is our sketch of the domain for this function here in the xy plane. We can also, of course, write this in our set notation. Our domain then, of course, is going to be the set of all points in the xy plane such that x squared plus y squared is less than 1. Moving on to another type of function that has some restrictions on it. Here we're going to sketch the domain for the function f of xy is equal to the natural log of x minus y. When we have a logarithm of some quantity, remember we can only take logs of positive numbers, so whatever's inside there needs to be positive. And the way that we write something as positive, we write that thing greater than 0, so the inside of our logarithm, x minus y, should be greater than 0. If we go ahead and do some adjusting here that makes it look like something that's easier to graph, maybe moving the y over to the other side, adding it to the other side would give us that x is greater than y. And if we turn that around, if you would prefer your y on the left side, then that would tell us y is less than x. So we could go ahead and say in our set notation, the domain is going to be the set of all points in the xy plane such that y is less than x. Now thinking about this y less than x, let's think of it as y equals x for now, and then we'll worry about the less than after that. So if it was y equal to x, that is a line through the origin with slope 1. So this would be y equal to x here. That's the graph of that. Now we don't actually want it to be equal to x. We don't have an equal bar here. We want it to be less than x. So it's going to be on one side or the other of the line. So since we don't actually want this line, what we'll go ahead and do is make that a dashed or a dotted line, saying that we don't want to be exactly on the line. And then since its y is less than x, we'll go ahead and shade below our line here. Since we're solved explicitly for y, you can see that this region under the line in the xy plane is our domain for the function. Looking at our final example here, sketch the domain for the function f of xy is equal to e to the negative x squared minus y squared. And this looks a bit more complicated than the others, but it turns out this is actually perhaps the simplest one of all. When we look at what's going on here, we have an exponential and we just have some square terms in the exponent. So squaring terms, we can certainly square any number, positive terms, negative terms, 0. So anything will work for x and y there in the exponent. And we can also take exponentials of any number as well, right? We could take e to a positive number, e to a negative number, e to the 0 would just be 1, right? So this could be anything as well. So looking at all of our operations in the formula here, none of them have any restrictions on them whatsoever. That means any x comma y will be able to plug in and get some value. So that really means that we actually get the entire xy plane as our domain. There are no restrictions whatsoever. So the entire plane is our domain. We might also go ahead and say that the domain is equal to two-dimensional space, in other words, R2. All right, everyone, hopefully this gives you a good start to your functions of more than one variable and finding domains of functions of two variables. Thanks for watching. We'll see you in the next video.